All right. Good morning and welcome everybody to the TerraTherm webinar series. This is our monthly webinar series, and today's webinar is entitled The Real-Time Fourier Transform Infrared, otherwise known as FTIR, Monitoring of Extracted Vapors at an In-Situ Thermal Remediation Site. My name is Alyson Fortune. I'm a senior scientist with TerraTherm. So let's get started. A bit about me. I am, like I said, a senior scientist with TerraTherm. I've been here just over three and a half years with TerraTherm, and I have over 15 years experience in the environmental industry. I have experience with source testing. I worked for analytical laboratories for a number of years and for an environmental consulting company. I have a bachelor's of science in environmental science and a master's in atmospheric science. And one of my roles here at TerraTherm, I have been in charge of the FTIR instrumentation and its use at our sites. The agenda today is I'm going to present a case study about a site where we use the FTIR very successfully, and it proved to be a wonderful tool for us. So we'll go through that case study, the site background. I'll explain a little bit more about the FTIR and the associated equipment that we typically use with it. We'll go through this specific case study, how the FTIR performed, and as well as lessons learned, and then finally wrapping it up with conclusions. As I mentioned before, there will be a question and answer session at the end, so feel free to submit your questions in the questions window on the webinar. And when you exit the webinar, you'll also have a post-webinar survey come your way. So please take the time to answer those quick questions, and we'll appreciate your feedback. So jumping into our site where we used the FTIR a few years ago, this is a confidential site in the southeastern United States. It was about 70,000 square foot treatment area in the subsurface, a site contaminated with chlorinated solvents, primarily trichloroethylene, also associated breakdown products. This was a combination site where we were both implementing in-situ thermal desorption or conductive heating technology combined with steam-enhanced extraction in certain areas of permeable geology. The treatment area consisted of approximately 35 multi-phase extraction wells and horizontal vacuum extracted wells. The contamination was to an average depth of about 41 feet below ground surface. TerraTherm was designing and constructing and operating this combination thermal remediation system, which was a supplemental remedy for the groundwater recovery and treatment system that was operated by others. We had performance criteria which was based on temperature, reaching certain temperature goals. And you can see a photograph of the part of the treatment area. This was somewhat unique in that the treatment area was both inside an existing building as well as outside an existing building. So the photograph you're seeing there is inside the building that was on site. Other than that, I'm not really going to get into a lot of the details of the remediation and the design and the subsurface geology, as this presentation is more focused on the FTIR and the monitoring of the vapors at this site. Here's just a basic schematic of our general remediation systems. In the center of the screen, you can see our heaters going into the subsurface and a network of vapor and groundwater extraction wells, shallow vapor recovery wells. We have got the power systems on the left-hand side of the screen feeding into the treatment area. Then coming from the treatment area, the black lines represent the vapor recovery manifold system. And then on the right-hand side of the screen, you see the treatment, the above-ground treatment process. So what we're generally talking about here for the FTIR monitoring in this case study, we're focusing on the treatment equipment area. So we had extracted vapor monitoring of the vapors going into and coming out of the treatment system, which in this case was a thermal oxidizer, and there was additional sorbent media backup systems. And then we also did some headspace monitoring over the liquid treatment vessels as well. This FTIR system was used exclusively to measure vapor. So that's a very common question that I will get is, can we use this system to monitor liquids in the wastewater treatment side of the treatment train? And the short answer is no. This system that we have is customized to monitor vapor. That being said, there could be a system constructed to monitor the liquid system, but this system that we're talking about today is primarily for vapors. So you can see the stars represent, portions of the treatment process where we were monitoring the vapors. You can see that lone star all the way out on the right is we were also monitoring the ambient air in the work zone for health and safety purposes. So just to go over what the FTIR is, here's a photograph of the unit in its NEMA enclosure. And FTIR stands for, like I mentioned before, Fourier transform infrared spectroscopy, and this is a real-time analyzer. The Fourier transform portion of the word refers to an algorithm that is used for calculation purposes, and the infrared spectroscopy is the actual measurement technique. What this is able to do is it's able to provide real-time and continuous monitoring of the vapor at our treatment sites. So unlike our traditional means of monitoring using field screening tools such as a photoionization detector or PID, or a flame ionization detector, an FID, or a 4-gas meter, or something of that nature, this has the advantage that we are getting speciated data for individual components and not just a total VOC number. So we're able to real-time see the individual components of interest. Similar to those other screening techniques that I mentioned, the FTIR should be also considered a screening tool, and it has a similar range of detection. So we're talking about kind of single-digit ppm detection limits. One of the main advantages of the FTIR is that we are able to simultaneously measure concentrations of various components that normally would require us to have multiple instruments or multiple lab analyses to measure all the different components. So for example, we can not only measure volatile organic compounds, but we're also able to measure things like methane, CO2, carbon monoxide, HCl, hydrochloric acid, percent water vapor, things of that nature as well, things that we would normally require many different techniques and many different instruments are all combined into this one instrument here. So you can see this cabinet is about 6 feet tall and is on a standalone skid by itself. I'll have some more photographs and schematics of it in a minute. Coupled with this FTIR instrument, we utilized this multi-point sampler and conditioning system, otherwise known as the MPS. What this allowed us to do is cycle through all the various locations that I had starred on the previous schematic by programming a sequence so that it would cycle through and start with one monitoring location, then after a set amount of time, switch to another sampling location, and so on until it cycled through all of them, and then it would repeat the sequence. The operator has the ability to manually change the sequence as needed. This really was a great tool for our site operators. If they made an on-site change to the treatment equipment and needed to just check right away, did I is this right? Are we good? Are we bad? They can immediately change that multi-point sampler to monitor whatever location they are interested in. The other function of this multi-point sampler and conditioning system was to control excess water vapor. Now, the FTIR is actually really well suited to monitor vapor at our remediation sites. It can handle hot vapors and wet vapors, and that's pretty much what we're dealing with most of the time at a thermal remediation site is hot, wet vapor. FTIR instruments are routinely used in other industries, such as industrial processes or chemical manufacturing, things where there's a set process where we need to have a quality control or real-time monitoring of a smokestack, that sort of application. To our knowledge, this is really the first implementation of a system like this for a short duration remediation system like ours. That being said, even though the FTIR can handle hot, wet vapors, we did want to control, have some gross excess water vapor control. So we had this knockout system to condition the vapor going into the FTIR so that the vapors would come from the various sampling locations throughout the treatment area into the multi-point sampler and then into the FTIR. So there's a photograph of the multi-point sampler and conditioning system. It's a little bit hard to see here, but you can see kind of a little bit of all the different valves and those white boxes inside the unit are refrigerated impingers that are knocking out the water vapor, and that water is then condensed, and then the water would be plumbed back to our liquid treatment system. Here's just a general schematic showing what I sort of just described, in that the vapor is coming from the well field and the different monitoring points. So we had before the thermal oxidizer, after the thermal oxidizer, in various, the vapors coming directly from the well field. We had the headspace of a liquid treatment vessel. Like I said before, we also were monitoring the work area. So all those different monitoring points would come into the multi-point sampler, and different valving would switch on and off such that, you know, one of those locations would be plumbed over to the FTIR at a time. All the vapors would go through this cooling step and knock out the gross water, as I described it previously. And then from there, it would travel from the multi-point sampler to the FTIR via a heated sample line. That heated sample line has the ability to be maintained at a couple different temperatures. We ran it at the 191C temperature. And then from there, the gas goes through a flow-through cell and is analyzed, and the discharge would go back to the vapor treatment system from the unit. The FTIR is a non-destructive unit, so similar to a PID. So we did need to make sure that the discharge of the system was plumbed back to the treatment system. One other component to the FTIR skid was that we did have a zero air generator that's shown as ZAG, the ZAG unit and compressor. So there was a little compressor pulling in ambient air and going through a cleaning process to create zero grade air, very clean air, and that was used to create a baseline on the system, as well as to flush out the system in between the different monitoring locations. We had a setup where we went in increasing concentration order. So we started with what we expected to be the lowest concentrations, for instance, the ambient air, and we worked our way up to the highest concentration, which would be the vapors coming directly from the well field before any vapor treatment. And in between each of those locations, we flushed out the system with zero grade air. After the highest concentration, we had an extended sort of flushing period to make sure that that the system was baselined out again. And the system was actually very, very stable and was able to flush out. We really didn't have any problems with any type of cross-contamination during the course of the project. So what this was able to give for us was the continuous data all throughout the vapor monitoring and, like I said, the headspace of the liquid monitoring system. Here's an example of the data that we would obtain from the system on a real-time basis. This is showing trichloroethylene, which was the major contaminant at the site. And each of those different color lines is representing one of the different locations. So we were able to, at any point in time, go in and look at what the concentrations were at one given time, what the trends had been over the past period of whatever duration, a few weeks or months, real time to get this information. And the resolution of having this type of real-time information definitely proved to be an advantage, which I'll talk about later, as opposed to somebody collecting individual grab samples. So I'll quickly go over what the FTIR is and how it works on a fairly high level. Basically, we're using infrared light. So there's a beam of infrared light, and that's applied to the sample gas in this multi-pass sample cell. So on the right-hand side of the screen, you can see 4.3 meter gas cell. That is where the gas from whichever sampling location we're monitoring at the time, that will flow through the cell. The beam of light is applied. The sample path length is increased in that cell with mirrors. So basically, the light is bouncing back and forth off the mirrors to increase the path length and therefore decrease the detection limit. So there's a bunch of other optics and things that are in there that are transforming that information into concentration base, power supply, pressure transducers, etc. But the basics of it are the gas is flowing through that gas cell, there's a beam of infrared light that's applied, and the path length is increased with the sample mirrors. And the infrared light will absorb in different regions. So the different components in the gas stream will each absorb infrared light in various spectral regions based on their molecular structure and chemical functional groups. So this figure here is just an example. This is not one from our site, but this is just a theoretical example showing in different colors the different spectral regions and the different sort of fingerprints or patterns that different contaminants will display. So you can see the black lines are representing water. So that's you can see that water absorbs in the 4,000 to 3,500 wave number region, as well as maybe 2,000 to about 1,250. And you can see that a lot of these components overlap and there are potential interferences, but the key is if you can find a region that is not impacted by whatever components are in your vapor stream as interferences, then that can be used successfully for quantitation. There's also a number of things that the software can do in terms of background correcting and such. So even if there are overlaps, it can still quantitate accurately. So this also shows, this is also a great figure to show the variety of components that can be measured all at the same time with the same instrument. So like I said, we have water vapor, methane, CO2, NO2, SO2, carbon monoxide, hydrocarbons, ammonia out there. All of these things can be measured simultaneously if we're set up to do that. Each component has this unique spectrum. In fact, the FTIR, I believe, is one of the only instrumentations or documentations that are allowed in a court of law for definitive evidence along with mass spectrometry, in that because we have this unique spectrum for each individual component. So it's an identification tool as well. At our project site, we chose to really challenge this instrument and look for as many things as we possibly could. So we looked for 10 individual VOCs. Like I mentioned, the TCE, which was our main component of concern. We had a number of the chlorinated breakdown products associated with TCE, and there was also a little bit of PCE there, the tetrachloroethylene. We also had 1,4-dioxane present on site, so we did look for that in the vapor phase. At this particular site and under these conditions, we didn't see too much of that in the vapor stream. We also had some BTEX compounds, so we were looking at toluene, chloroform, methylene chloride, a few other components. And then, like I said, we also were able to monitor these other inorganic and light hydrocarbons. So water vapor, we did measure HCl, carbon dioxide, methane. Then we did set up one parameter which we called hydrocarbon, and that was supposed to be analogous to a total VOC number that we would get from a PID. So we were looking at any compound that had a response of carbon to hydrogen, a carbon to hydrogen bond would respond in that hydrocarbon category and was summed up as just a general trend. And that was the purpose of it. It wasn't supposed to be super exact and quantitative, but more just for trends and seeing, are the concentrations going up? Are they going down? Is something breaking through? Is it not? So those are the items we were monitoring. I will note that a few of these components that are especially water soluble, so the hydrochloric acid vapor and 1,4-dioxane, we weren't expecting to see a huge amount of those get through to the FTIR because of that multi-point sampler conditioning system, where we're knocking out a whole bunch of that water vapor. But this was, a pilot installation for this instrument. The first time we were using it, we just wanted to challenge it and see if we could see these components in the stream. So moving on to some of the operational advantages that we saw while using this instrument at the site. One of the biggest pieces of feedback that I received from our site operators at this particular site was that they loved it because it really gave them real-time knowledge to evaluate their changes made to the system so that they could optimize it real-time and know what they were doing. So if they had to bypass something, if some part of the treatment system was down, they could easily just use the FTIR and just look on the screen to see what the concentrations were, as opposed to other traditional ways that we have typically used at other sites, like using a handheld screening device where you had to go collect some type of Tedlar bag grab sample, go back to the job trailer, calibrate your PID, screen it that way. This was much faster, and it was real time, and they could see changes happening real time as opposed to just collecting discrete grab samples. And obviously, it was much faster than if we were to collect laboratory samples and send them off for analysis, where we're waiting a matter of days or even weeks for those results. So theoretically, we would be able to evaluate breakthrough on vapor treatment media. We were able to monitor the work zone continuously. So if there were ever concerns that our workers were being exposed to something of concern, then we were able to see that right away, what they were being exposed to once we set it up for the compounds of interest. And overall, the general consensus was that the FTIR was much faster and easier and more reliable than the handheld PID. The FTIR system was sent off for initial calibration with the vendor, and it's typical for those types of systems. They have very little drift, so it's very typical for those systems to just require a baseline or a zeroing and not necessarily a span calibration check. on any kind of a regular basis. So it was really just set it up and forget it. Set it up and have it in line. Make sure you're zeroing out and getting your good baseline for the spectral comparisons, and otherwise it was just set up, and our operators really had minimal maintenance on the equipment. And there was definitely less influence or issue with humidity. I know that's a challenge at many of our sites with the PID monitoring, is the effect of humidity on that piece of instrumentation. The FTIR was much better able to handle that. So here's a couple screen views of what the system looked like. So the figure on the left was what our operators would see. So it was very user-friendly and very straightforward. They would see at any given time what the concentrations were. So you can see zeros across the board, 0, 0, 0, all the way down. So that was during a blank or a 0, or maybe perhaps the ambient air monitoring. So it would quickly and easily show them by what they could walk by and just look at the screen and see what the concentrations were at any given time. If they were interested, or in more likelihood, if I were interested, I could actually go into the raw data, and that's the figure that's shown on the right-hand side. So I could open up each of those scans that are being done on a real-time basis to see what it is that we're seeing in the vapor stream at any given time. So all that raw data and information was available for review if needed. So if we were seeing some kind of value that was not as expected, we could go in and look to see what was going on. So I would routinely dial in and just spot check these spectra and make sure that we weren't seeing any kind of really strange interference or something that that was not as expected. So there was definitely a learning curve for this particular site, as there would be for any new site, to know what's normal, what's the normal vapor look like here, and that way you're able to identify when something is out of the ordinary. But for the operators, very easy screen view there. Then the multi-point sampler had a similar screen and easy-to-use, user-friendly software. So this would tell the operators which of the locations was being sampled at that given time. And it would give you, different temperatures and such along the way for troubleshooting purposes. So they would look at this screen to know which sample location was being sampled. If they wanted to manually change it, so that because they wanted to check something, they could do that in this screen and then go back to the other screen to look at the concentrations. For this particular site, we also had all of our FTIR data going through the thinkthermal.com website. So real time, anyone from the project team who had access to the thinkthermal.com website, this site web for this particular job site, could access the FTIR data as well as other data, temperature data, and other related data to see what was happening on a real-time basis. Now, this was an extremely powerful tool for us here in the office supporting the field efforts. We were able to easily just quickly see what was going on, dial into the system, see what was going on. What this also did in this particular instance was give the client a real sense of ownership of this site, and it allowed them to address concerns of various stakeholders. So this particular site originally had a requirement to monitor the effluent vapor coming from the thermal oxidizer out the stack on a daily basis. If we had done daily laboratory samples on a fast turnaround time, that would have been extraordinarily expensive and just a lot to manage. having the FTIR monitor the stack real-time, 24/7, gave everyone that sense of comfort that, you know, our remediation system was not emitting anything to the environment or to, you know, it also allowed folks to monitor things if there were odor complaints or anything of that nature. We could quickly go on and say, yep, you're smelling something, but it's not related to our site because we're monitoring the concentrations real time. So that was a great tool in this particular instance, and another potential feature that could be worked into other sites as well. The one challenge with monitoring our vapors at our thermal remediation site is that the vapor composition is changing over time. And this is a key difference between how we're using the FTIR instrumentation versus a lot of other industries. A lot of other industries are using the FTIR as quality control or monitoring for a system that is pretty static. It's set up, there's always a certain contaminant mix or chemical composition within a certain range, and you know what to expect, and it's not really changing. That's generally not the case at any of our thermal remediation sites. We always are encountering contaminants that perhaps we didn't know were there initially because they weren't looked for. Also, just inherently, the vapor composition is changing over time because as we're heating up, we're getting fractionation and volatilization of different components at different times as we reach different subsurface temperatures. So that presents a challenge with the FTIR in that we have to be constantly making sure that we're not introducing new interferences that are interfering with our compounds of interest. So what we did at this site was we verified the FTIR results with lab data on a regular basis. And the purpose of that was to identify if there were any additional interferences that were causing a positive or negative bias with the results we were seeing on the FTIR. So we collected SUMA canister samples on a regular basis, sent them off for TO15 analysis to get a full suite of speciated VOCs. So when we had all this data, we were able to compare what we were seeing in terms of concentrations in the canister versus the FTIR. We did also maintain our sort of normal protocol of the PID monitoring at this site as well. So we had all three pieces of information here. So you're able to see that the PID versus the FTIR, that total hydrocarbon measurement, was matched up fairly well. Definitely at lower concentrations, you're closer to that one-to-one line. The one-to-one line is shown as a red dashed line, and then the linear regression of our actual data is shown as the black line. So you can see for the PID versus FTIR on the left-hand side of the screen, at some lower concentrations, you know, it lined up fairly well with one-to-one, and then as we get to higher concentrations, there's a little bit more spread. I generally attribute that to the inconsistency of the PID readings. Not only is it just a grab sample collected in a Tevlar bag, screened with the PID, as we all know, anyone who's been out there, there's always issues with the PID, and we have different site operators running that from day to day, and they might have some small variations on how they're doing things. So that spread didn't necessarily surprise me too much. The canister versus FTIR data, if we're looking at some of the total hydrocarbons there at the site, I'm sorry, I said total hydrocarbons, I just meant total contaminants at the site, total volatile contaminants at the site. Those matched up very well, in fact, better than the PID. You can see that there's, it's definitely not quite the one-to-one correlation there, especially as we get to the higher concentrations, but up to about 50 ppm or so, we're seeing really good linear comparison there. And I attribute the difference in the concentrations between the FTIR and the canister at the higher concentrations due to the dilutions that are needed when we're doing the canister analysis, which is generally meant for parts per billion level. So when we get to high ppm level, the lab has to do extra dilutions and multiple sort of preparation steps, each of which add a small amount of error with that result. So again, that didn't necessarily surprise me to see that level of variability there. So we were able to compare individual components from the FTIR versus the canister. Some compounds matched very, very well and were very consistent. TCE, which is shown in this figure here, was one of the more consistent ones. Again, very linear at the lower concentrations, and then for some of the higher concentration lab samples, when we were at our peak of mass removal there and higher concentrations, again, the lab had to dilute those samples, so it's adding some error there, and that's why we're seeing some spread and movement away from that one-to-one line. Many of the compounds that we were monitoring at the site had fairly low concentrations near the limit of detection. Some of them were, detected at very low levels in the canister, but were below the limit of detection on the FTIR. And there were a few compounds where we did observe some interferences from the sample matrix. And we were able to identify that because we did routine monitoring with the canisters. So we knew, hey, we're seeing, a few ppm of this contaminant on the FTIR, but we didn't see it in the canister. Why is that? So we were able to observe interferences that way and piece together based on the other contaminant data that we got from the canisters to try to figure out what was interfering. One of the contaminants and one of the lessons learned from this exercise was the interference of water vapor. And we learned that the water management was essential when we were monitoring for vinyl chloride. So vinyl chloride was one of the chlorinated breakdown products which we were monitoring. There is a specific interference with water vapor. So you can see it's a little bit hard to see on this figure, but if you have a big screen like me here in the office, you can see it okay. The water vapor and then also CO2 are shown as that olive green line and pattern. And you can see that underneath in the hot pink is the vinyl chloride response. And you can see that it's sort of buried there underneath that big response from water, right around 1600 wave number. So what was happening at this particular site was we had a few incidents where the multi-point sampler and conditioner was not able to handle all the water vapor that it was presented with. This was a site in the southeast and is very hot and humid. And that excess water vapor getting through to the instrument created a false positive for vinyl chloride. So we were seeing vinyl chloride show up on the FTIR when it wasn't there. We were able to confirm that with canisters as well as Draeger tubes and some other real-time techniques like that. But we were able to see that interference from water. So how we would alleviate this in the future would be we would try to look for a spectral region that was minimally affected by that interference from water if we're looking for vinyl chloride and that was of particular interest, and or we would definitely up the water management and make sure that those cooling knockouts were sized appropriately. We had a couple instances where they were overloaded and we had more water vapor than it could handle at a time. So that was definitely a valuable lessons learned there. You can see here that there appeared to be sort of a water, what I call the threshold. And the horizontal red line is showing the limit of detection of vinyl chloride. So you can see, and then the x-axis is showing the percent of water vapor. So you can see as we were below around 0.75% water, definitely below 0.5% water vapor, that water vapor was not contributing to any sort of a false positive of vinyl chloride. We were at the limit of detection or below. Between 0.5 and about 0.75, things got a little crazy in that we had some varied responses. Sometimes it was still at that limit of detection. Sometimes you were seeing up to 8 ppm vinyl chloride as sort of a false positive. And that was, a limitation of the software being able to correct for and subtract out that sort of water background that was present. And then once we were over that 1% water vapor, it almost went up in a near linear fashion. So it was definitely, you can see the influence of that water vapor had a linear response in the vinyl chloride. So again, the lessons learned would be either select a different region of, so that we're looking at a different spectral region for vinyl chloride that doesn't interfere with water, and or make sure we really have our water management down, so we're down in that 0.5% water vapor range so that we eliminate that interference. And again, this was a specific interference with vinyl chloride. It did not affect any of the other contaminants that we were looking for at this site. So like I said, the lessons learned, the lab sample correlation was very important. It allowed us to identify these additional potential interferences, as well as make sure that if we had these kind of false positives with the vinyl chloride, that we really didn't have vinyl chloride there. I didn't really talk much about it, but there is a daily reference spectra measurement of the zero air, sort of a baseline or zeroing of the instrument. That definitely proved crucial to having accurate sample concentrations. If your reference spectra is not the clean zero air and it happens to be something else by mistake, which happened a couple times to us, it throws off the concentrations because it's comparing your sample spectra to this other reference spectra, and it throws off your quantitation wildly. So definitely having that accurate baseline measurement proved crucial, and that is something on our system that can be set up automatically to do on a routine basis without the operators having to do it themselves. We are definitely better able to track our progress in the project in terms of the mass removal. We also had, since this was a combination steam site and ISTD site, we had steam pressure cycling near the end of the project. We were definitely able to see the results of that in some peaks at the end of concentrations coming through as we cycled those steam pressures. We were able to see that real time. It's also important to have a good initial characterization of the sample stream or anticipated components. So that goes back to the information that you have about the site and the characterization of the site before we even start the project. What components are going to be there, what's in the subsurface, what's going to be coming out as we heat it up. So it's really important to have that information as well. One other thing that I will note is that for this particular site where we were focused on using the FTIR really as a tool for measurement of the vapor going through the vapor treatment system and optimizing the vapor treatment system, this FTIR system could also potentially be used for monitoring of the extracted vapors in different regions throughout the treatment zone, the treatment area. So for instance, if there were multiple zones throughout the treatment area, we could monitor manifold legs from each of those. And then as the mass recovery dropped off from those zones, we would have the ability to know that real time and potentially shut off, heaters and shut off treatment in those areas which were sort of done before other areas, so that we could save money on the overall cost of the project. One of the other main things would be to optimize something like a carbon system usage. So we'd be able to monitor the concentrations in the vapor going into and going through those carbon beds to predict when we're going to get breakthrough, to optimize, loading up of that first bed, so that we're not just responding to an exceedance and changing out all the vapor carbon. We're really trying to optimize the usage and minimize the cost and the waste of carbon in that kind of a situation. So the FTIR definitely is a great tool that could be used for any of those benefits. And I believe that is my last slide here. Well, I've got one more summary, I guess. So we implemented this novel use of the FTIR system at our in-situ remediation site. It contributed to the overall success of the project, and we met all our remedial goals. Like I mentioned, it allowed the client to view the real-time concentrations from the stack, which was a specific desire for that particular site and that particular client. And it allowed us to optimize our extraction and treatment systems, like I just mentioned. For other sites, we'd be able to optimize shutting down various locations throughout the treatment system as they finished up as well. So I think with that, I will open it up to questions. If anyone has questions, feel free to type them into the question field, and I will